Uh, Hello, everyone. Um, I am making this recording today because the recording from my lecture yesterday, unfortunately, we realized halfway through class I was muted. So there was no audio for the lecture portion of the talk. So thought that I would go back and re-record some of my lecture here. I'm only going to cover just the slides beginning here and not the in-class activities. We were able to get the sound back on for the in-class activities. So there is a video for that already on Canvas, separate video. The audio is not great, but it should serve a purpose. And if you have any questions, let me know. But for now, let's go through a lecture on data visualization. So today I'm going to be talking to you about data visualization, how to make pretty plots with your data. It's something that all of us we'll end up needing to do at some point in our career as scientists and researchers. And it's an important mix of a little bit of science and a little bit of art. So we're going to get into the kind of that today. First, before we do so, I wanted to kind of introduce myself a little bit. I know I did a short introduction on Monday in the class for the TA session, but I'm Jim. I'm one of your TAs for the course. I'm actually a fifth-year student in the genetics program here at Emory. I study the computational immunology, gene regulation, looking at functional sequencing data and analyzing it from a dry lab perspective. And so what that means is that I work with R and some other programming languages now on a daily basis. And what's relevant for you all is that I didn't necessarily know how to do all that before I started at Emory here. So I started back in 2019, and one of the first things I sought out to do was to teach myself R. So I'm a self-taught coder. And I found that I particularly enjoy it. And like I said, I use it every day now. And I've become what I would call more or less fluent in R. I'm working on that as well as in the Python language, getting a little better at that for some machine learning applications I'm working on at the moment. But if you want to know anything more about me, I have a website. You can see the link here. If you want to, you should also think about building yourself your own website. As a PhD student, it's a valuable tool for sort of self-promotion once you get to the job kind of search end of things, where I'm getting to now. So having this as a kind of place to showcase some of your work or interest is always a good idea. So for today, this lecture is going to cover a few main points. Firstly, the question of why look at or visualize data? Why do we want to do that? What's the point? Why can't we just, calculate some statistics? Why do we need to make graphs? And then the second kind of main question is, how should I look at data? It's actually a fairly, like I said, complicated mix of a little bit of an art and a little bit of science. There's a lot of sort of design thinking that goes into it. That's not something we're always taught as scientists. So thinking about that is kind of a fun and somewhat creative aspect of our work, which I think is really important. And then the last part of today is going to get into ggplot. And so ggplot is one of the main packages used for data visualization in the R programming language, probably the most popular one. It's quite easy to use, actually, and we're going to teach you how to use it here today in detail, so you should be able to use that through the rest of the course. Okay, so part one, why visualize data? So a few answers to this question kind of come to mind. One is to explore or to better understand your data. This is something sometimes termed exploratory data analysis, or EDA. And you'll see why this is important in a second. And there's another reason. We may want to visualize data to convey a point or make an argument. And this may feel a little bit strange for a researcher, but the fact is that anytime you're making a figure for a publication or research journal, you are in a way trying to make a point. You're trying to argue that your interpretation of the data is the correct interpretation. And so using visualizations to serve this purpose is also equally important, as well as the kind of first exploratory understanding principles of it as well. Okay, so visualizing to explore data. If you are seeing this for the first time, I want you to kind of take a second and look at this, figure here, this GIF that's playing. And what you're seeing is a scatter plot of data points on the left, as well as what we call summary statistics on the right. And summary statistics is just a fancy word for the mean, median, standard deviation, those sort of things. Um, and take a second to see what you think. All this data is changing as you see the kind of dots move around on the scatter plot. But you'll notice, if you look closely, that the changes in the summary statistics are pretty minimal, if anything at all. And so what this is saying is that sometimes when we have a large, complicated data set, our instinct is to, it's too big sometimes to actually just look at in like a table form, or too big for an Excel spreadsheet. So oftentimes we reduce to the summary statistics. We look at the mean, we look at the standard deviation, and try to use that as a way to understand what the shape of the data is. Unfortunately, as you can see here, if you do that, you run the risk of missing patterns. There's actually, our human brains are way better at finding patterns in visual data than we are in numbers. And so you could be missing the dinosaur hiding in your data if you weren't able to actually visualize it. So it's an important tool for understanding your data in another dimension that's not possible through numbers alone. This is an example of how to visualize to convince or make an argument. So I'm showing you two plots here. On the left-hand side is more or less a heat map showing the incidence of measles in the United States across time on the x-axis, and the y-axis is indicating the different states of the different parts of the country. And you see this big vertical black line indicating the time in history when the measles vaccine was introduced. I'll let you interpret that yourself. On the right-hand side is what I would consider one of the probably the more famous graphs or data graphs of our current age. Believe it or not, this is, I believe, from the original Pfizer COVID-19 vaccine trial. And what you're seeing is the x-axis is representing time during a clinical trial. The y-axis is representing cumulative numbers of cases of COVID in two different groups. Either the blue is the group that received the vaccine, and the red is the group that received a placebo. So again, if this is the first time you're seeing this presentation, take a second and try to see if you can answer, maybe pause the video and answer the question of what sort of point do you think I'm making here? What is the argument I'm trying to make? And come back once you have an idea, and I'll see if it's kind of the same idea I was thinking. Okay, so the point I was trying to make with this is that vaccines work, right? So the data is presenting that in a pretty convincing argument, I'd say, given these two visualizations. And surprisingly, this is an argument that continues to have to be made. And even to this day, it seems a little bit less kind of on the top of our minds after the pandemic has ended a little bit. But still, vaccines are important. And you should go get your flu vaccine, as well as the booster for COVID. It's coming out in September, so keep that in mind. Vaccines work. Here are a few examples of when data visualization goes wrong. So again, if this is the first time you're seeing this presentation, I want you to take a second and look at both of these and think about why these may not be the best examples of data visualization. And kind of then come back, pause the video, come back, and I'll explain it in a second. Okay, so the graph on the left, the feedback we often get about this one is that it's just busy, right? There's a lot going on. There's a lot of information crammed together in one plot, and it's not exactly easy to interpret why there are lines and bars all overlaid on top of each other. Another kind of issue is that these dual y-axes are sort of kind of conflating two completely different scales. And so it's suggesting to the audience that there's a similarity between, say, 9,000 and 12% that isn't really the case. That's just an arbitrary choice made by the plotter. So it's a little bit misleading as well. And also it'd be better to kind of make a different version of this graph using what we'll call faceting, where you take two separate versions and you would maybe have the bar plots as one and the line plots as another with their independent scales that will allow people to kind of understand this data a lot more clearly. Okay, the one on the right is an example that we'll get into in a little bit, talking about perception and what works or what doesn't work for people trying to perceive differences in data. So it's actually extremely difficult for people to interpret these sort of 3D volume type representations of data. Um, Someone also in class made an argument that the labels aren't very big; they're pretty hard to read. That may be just partly how I set it up in the slide, but again, font size is important. Keep that in mind when you're making your own figures. But the general point I wanted to make here was that the 3D visualizations, while they might have been fashionable at one point in Excel, maybe a long time ago, uh, are really bad actually for accurately conveying your data in a way that people can understand quickly. And it's really hard to see what they were trying to say here with this data using this kind of 3D representation. Okay, so now we're going to move on to part two, the topic being how should I visualize data? And I want to kind of start with a quote here from the great Uncle Ben Parker from Spider-Man. With great power comes great responsibility. As you kind of saw in the earlier section, we can use data visualization to do some powerful things, to learn more about the world or the data we're working with, or to convince people of things. And you'll learn kind of at the end of this lecture about the possibilities using programming to generate data visualizations and how they're almost endless. You're in some ways only limited by what you're able to kind of your knowledge of the programming language as well as your creativity. And so that is a great power. But I guess, like we say here, it comes with a responsibility, and there are ways to do this well and ways to not so much do it well. And it's important to keep that in mind as you're going through your journey as a researcher or PhD. I'm going to introduce this concept of the pillars of good data visualization. And we're going to go into details about each of these 5 pillars. This ranges from everything from showing the data honestly and accurately, thinking about perception, the way people perceive things on a visual format, reducing clutter in your graphs, using color in smart ways, as well as using creativity to sort of get people's attention. So let's just jump now into the first pillar. So this pillar, show the data honestly, is part of what's kind of become a new requirement in a lot of journals these days for research publications. That you'll notice here in this publication figure that they're just demonstrating the concept of what you lose when you only show a summary statistic bar plot. So panel A here is showing a bar plot of the data with 2 different means, as well as what I assume are some sort of standard deviation or other kind of confidence interval metric. And what they're saying is that behind these bar plots, because you can't see the individual data points, you could actually be hiding many different sorts of distributions of the data. B, C, D, and E all represent different types of distributions that could generate the exact same bar plot if you just look at the summary statistics. And what you're losing by only looking at the bar plot and not showing all of your data is the ability to critically assess whether or not you think these means are accurate representations of what you think you're trying to say. It may be that they're kind of generated a little bit by an outlier, for example, that's skewing the mean. We know that means are very sensitive to outliers, so they might be skewing that mean a little bit higher in that group. It also could be that you have a bimodal distribution, and so there's actually multiple groups within each of these 2 columns that you may want to pay attention to and learn more about in your data, or maybe differences in the size of the populations you're looking at that kind of give you the certainty, or we'll learn about the central limit theorem later in this class about how that's important for generating power. And none of this is interpretable from just a bar plot. And so to enable to kind of have your readers make critical assessments of the data, most journals now require that anytime you show a bar plot, you also show every single individual data point that goes into that bar plot. And that's for this exact reason. It allows kind of reviewers and readers of the paper to understand the data better and to make their own critical assessments of what the data is saying. And to prevent you from hiding things that maybe are not a convenient interpretation based on what you're trying to say. Okay, pillar number 2, think about perception. We talked a little bit about this with those 3D volume charts, but it's actually really important when you're making data visualizations to think about the way people's brains work when they're interpreting visual art, designs or figures. And there's actually a big difference in the sorts of ways your brain can interpret accurately differences in different modalities of a figure. So this chart here is showing kind of the gradient based on a lot of studies done in sort of the neuroscience world of how accurate people are able to interpret differences across different aspects of a chart. So on the top here, you see the things that are the easiest for people to interpret. And these could be things like positions along common scales, like this, length of a bar or the point of a line on a scale. And as you get kind of lower down in this kind of gradient here, you start to see differences, like it's a little bit harder for people to interpret differences in length that may help you show things. And when you get to the very bottom, you start to see the things that are the most difficult for people to perceive. These include volume. It's actually very hard, as I said, for people to interpret volume differences in a 2D representation, especially. And color. Color is actually a very difficult thing to, kind of map to a accurate value. And if you're looking to do that with color, it's usually not the best choice. So again, it's important to kind of decide what type of chart you're using based on this idea of perception, and to try to maximize the accuracy of the way people can perceive data and what could help them understand things the most quickly with the least amount of effort. One thing I want you all to start thinking about doing is thinking about your graphs, your figures in terms of channels. So what this means is you can think about a channel as more or less a place to put data, right? And so this is an example of a relatively complicated plot that actually has 4 separate channels of data at the same time. And they've done a relatively good job, I'd say, of putting this all together into a nice visualization that conveys a lot of information all at the same time. And so what I mean by channels, it can be things like axes. So channel 1 here is the y-axis, which is showing different states across the United States. Channel 2 is the x-axis, showing obesity rates. But in addition to that, you also have 2 additional channels. You have a channel for shape, where individual dots here are given different shapes based on the ancestry group they are referring to, as well as color. So color here is representing regions of the United States, the North, the South, the West. So if this is the first time you're seeing the presentation, take a second now to think about what you can kind of interpret from this plot, given the different channels. And then come back in a second and we'll talk about it. Okay, so one of the main things you can pretty quickly see using the power of the color channel is that there's a little bit of a higher trend towards obesity in the South, right? All of these blue lines are kind of clustering up towards the top. They seem to be ordered, those states are ordered by the obesity rate, more or less. Other things you can notice is the differences across the ancestry groups. You seem to have this difference of kind of minority groups being higher in the obesity rate in the South. In the West, it seems to kind of switch. You have more Caucasian individuals doing that. So there are differences that you can see all at the same time, as well as individual data from each state. And this is a pretty good example of using a lot of different channels at once to make a informative graph that's pretty, concise at the same time. Pillar 3, reduce clutter. So this is an example of a plot using some data we're going to actually play with in class, in-class activity, looking at Pokemon. And if you're not familiar with Pokemon, you're going to learn about it in your assignment as well. They're basically fictional monsters that people have come up with that have all these different stats, like attack or defense or hit points. And there's a lot of data we have on each Pokemon here. And obviously, this is not a very good plot. The reason for that is it's just extremely cluttered. We've tried to kind of label every individual Pokemon with its name, but it's really hard to see what's going on here. This is what's called overplotting, where you have a lot of things kind of layered on top of each other, and it becomes impossible to see individual data points. And this is a common problem that you face, especially with large data sets like maybe sequencing data or other sort of multi-faceted data, where you have a lot of points. And so it's really hard to kind of interpret what this data is saying if you can't really even see it because of the clutter. So what we can do is we can use different techniques to reduce that clutter. So here's one example that I came up with for how to kind of show this data in a little bit less of a cluttered way. One thing you might want to do is to remove a lot of those labels, because there's no way to plot them all at the same time and to be able to read every single one. Maybe you only want to label the outliers. So like Shuckle here is an example of a very weird outlier with only defense and almost no attack. And that might be interesting to you depending on what you're trying to convey here. At the same time, you can start to summarize some of the data. This is something called a density plot, a 2D density plot, which kind of shows where the density of the points is. Some people might be familiar with this from things like flow cytometry or other analyses it's commonly used in. And you can see here where the majority of the points seem to be falling in this kind of middle section here, but also sort of the distribution, if you will, in 2 dimensions of the data. You'll notice that I also am trying to preserve the concept of the first pillar of showing the data by keeping all of the individual points here. And to kind of help people still be able to read and reduce some of the clutter, I've done things like color those points a little bit lighter, kind of put them more in the background so that if you really want to see them, you can. You can see that summary statistic does match the data pretty well. But you can still see every individual data point if you need to. And so these are examples of things you can do using color, using labeling, using kind of selective places you want to put people's attention to reduce the clutter in your plot and to really kind of make your point a little bit better. Pillar number 4 is use color strategically. So in this case, I'm showing you one of the most famous data visualizations of kind of the modern age. Probably only oldest too, if not the oldest. This was created by a guy named Menard, who was studying Napoleon's march towards Moscow in Russia in the 1800s. And don't worry about reading any of this text. A lot of it is in French, so you'd have to be able to speak French. But what it is a map, and it's showing the location of various cities or towns in Russia along the route that Napoleon's army took towards Moscow. And you see 2 different groups colored in different ways. So this top group is the size, the width of the line is indicating the size of Napoleon's army as it advances towards Moscow. And then this black group is showing the size of that same army as he makes his retreat. And so if you know anything about history, Napoleon didn't have a very good time in Russia. It was winter. The Russians were very kind of burned pretty much everything along the way, leaving little to no resources for Napoleon's army. And it became a huge disaster for the French army as they advanced on Moscow. It came so close to taking the capital, but then had to pretty much just retreat. And you can see his army more or less dwindled to nothing due to deaths as well as just people leaving. So this is an example of using color in a way to kind of categorize 2 different groups, those groups being the advancing army and the retreating army. You can see there's a big difference in the size of the width of the line there. Another way to use color that's pretty effective is to highlight. So here I'm showing you some data with the metric called forced expiratory volume. This is actually a medical test that is done on people with a disease called cystic fibrosis. And so what it measures more or less is the amount of air volume that the person can expel from their lungs at a given time. And we're actually counting, following individuals in a huge data set here across time and measuring this metric. And what you can see on the left is if you try to plot every single individual and every single time point, it's impossible to see anything. The clutter problem is occurring, right? So what you can do is you can decide to focus, use your color changes to specify a single individual, as you are here, seeing on the right here. And by focusing people's attention on that single individual, you can still make the point that this FEV metric tends to go down over time, which is just unfortunately a consequence of the disease. At the same time, I've kind of, instead of removing all the other data points, I've kind of, again, sort of grayed them out, which helps to kind of still show the data and give people confidence that you're not hiding anything, but allows people to see beyond this tangled mess of black lines. So this is an example of using color to highlight a particular point you might want to make. One kind of aside, don't make rainbow clown vomit charts. The rainbow palette is not particularly good for several reasons. One, I don't think it's particularly visually appealing. People particularly hate this one clown here from a popular video game over the last few years, if you're familiar with Pietro. And I think the reason of that is it's just, it's too much, right? There are better choices you can make in terms of color palette that are a little bit more aesthetically pleasing and also easier to interpret, as we'll see in a second. And one recommendation I will make to you is whenever you start a new project, one of the first things you should do is decide on a color palette. There are various tools out there for designing color palettes of colors that work well together for maybe looking at categorical data with different categories. Maybe you want to represent some sort of relationship between those by the different shades of the colors you're using. There are definitely different ways you can kind of get creative with your color palettes and pick one and stick with it. So the point is you can then kind of make it easy for people that are following along and reading your paper for the first time to know that this color maps to that group and is consistently doing so for the entirety of your paper. And so that's a really important concept to get kind of into at the beginning and to just, keep as a nice way to kind of be consistent and help people understand these differences between groups a little bit easier. One of the reasons the rainbow color palette is not great is that it's not very good for people with color blindness. So one thing you need to think about when you're designing a color palette is inclusivity. We want to have our work interpretable by as many people as possible. And that includes people who may not have, the same sort of abilities as you or I, or maybe in a kind of specific group where they're limited in some way in their visual capacities. And so there are ways to account for this in your color palette. I use them to generate these plots here. You can see the original on the left, as well as two different versions of simulated what the color would look like if you had different kinds of color blindness. And you can see that it becomes a lot harder to distinguish, like especially this blue and purple here in this particular type of color blindness. And so if you're using that to kind of help people understand differences in your data, it may be really hard for somebody with color blindness. And you should try out one of these simulators. It's pretty easy. There are websites, so if you just Google it, you should be able to find it, and you upload a JPEG and it will show you kind of this version of it and what it looks like. So keep that in mind. There are also color palettes that are designed by others to be specifically good for people with color blindness. So it can be very useful. You can just choose one of those if you'd rather. The last pillar, get creative. So this is W.E.B. Du Bois, the great scholar, a local from Atlanta here. And what I'm showing you is a visualization he created for the 1900 Paris expedition. And so W.E.B. Du Bois studied the African-American population in Georgia in the 1800s. And he had a problem. He was going to this giant expo in Paris around the turn of the century, and he wanted to kind of share with everybody his data. He collected a lot of data on all the sort of economic and demographic information about African Americans after the Civil War, and was really trying to get people to pay attention to it. And he's done such great work that he thought that, he needs people to kind of see it. And so how do you get people's attention in a giant convention floor that will kind of make them stop and want to look more closely at what you're trying to say? And his answer to that was a series of visualization, this being one example here, that were extremely creative and are held up as one of the best designs for data visualization known today. And so this effectively on the left here is just a bar plot, right? But what he's done is he's taken this bar plot and he's converted into a very interesting sort of swirl design, showing you the differences across these values over time for individuals. And so the plot is a simple plot that most people know and are familiar with, but the fact that it's kind of in this interesting design, these were all handmade, of course, back in the day, and drawn and spent a lot of time on. But there's a lot of design artistry that's gone into it to capture people's attention and to get them kind of to come up to that booth at the expo and want to learn more. And I actually got the chance to see these in person this summer. They still are kind of kept in a museum, I think in New York was where I was. The originals, a person of them, were there on display, and it's really cool. If you want to learn more, I have a book of all the various visualizations that you can look through. Just let me know, you can borrow it. But he was one of the best examples of extremely creative ways to present data. If you're feeling a little overwhelmed by all the different opportunities for different kinds of plots, or maybe you're not familiar with all the different kinds of plots there are, I would recommend that you consult a chart library or atlas. This is one example with the link here that you can use. And what this is basically a place where any sort of type of graph is kind of collected in one place, and you can kind of peruse through it and kind of get ideas. The nice thing about this particular library is that it also, I think, includes example code for a lot of these plots in R. So if you want to kind of take some part of that code and apply it towards your visualization, you can use this as a reference to kind of get ideas. And so there are so many different kinds of plots. This is like violin plots, density plots, scatter plots, bubble plots, ridged line plots. There's a lot of creative ways to display data, and sometimes it's easy just kind of spend some time going through this and thinking about it a little bit more. If you are looking for more resources, again, this is kind of just scratching the surface of what is kind of the art or science of data visualization. Your textbook is a pretty good place to start. There are also some other books I've recommended here. I have a physical copy of this one. I thought it was a pretty good introduction to some of these concepts of data visualization, good and bad aspects, as well as this one as well, which I think is a bit more focused on R. So if you want to kind of know more, these are some places to start. There's also so many resources online, so feel free to look there. Okay, at this point in class, we would have taken a quick break, but we're getting into the third part here, talking about more the kind of nuts and bolts of how to do this stuff, right? So we're working in R in this class and teaching you how to use it. And one of the most popular visualization tools in R is this package called ggplot. So ggplot is a package designed for data visualization, and it's actually extremely easy to learn and use, and we're going to teach you it here today. You should know that ggplot is kind of your first introduction to what is called the tidyverse. So the tidyverse is actually a collection of packages created by a kind of consortium of people that all kind of got together and had some ideas about how they wanted to do data analysis and make it easy and intuitive for people to understand. You can kind of think about the tidyverse as similar to kind of the Marvel universe, right? So both are kind of a collection of distinct packages or distinct superheroes, but they all tend to work together. So in the case of the tidyverse, they're designed to work well together and use kind of the same core ideas. In the Marvel universe, they all kind of cameo in each other's movies and help to kind of get people excited about the overall universe. Both are extremely nerdy. They're also, of course, people who are just tired of these kind of franchise things and consider the Marvel universe is killing modern film industry. Some people are kind of getting tired of the tidyverse for that same way, but I would argue they're just mad at the success of it. So it can be a little bit polarizing, but it happens to be extremely easy to use and learn. So we are teaching you here today. Using ggplot2 in particular, it's pretty amazing the sort of scope of what is possible, right? So every single visualization here on the slide has been created by somebody using ggplot in R. And this ranges from everything from simple scatter plots or box plots or histograms to more complicated versions of those. They're using interesting color changes and ridge diagrams. Geographic data can be presented using ggplot and R. And you can even kind of combine all these into these large scale infographics, which kind of show a lot of data in interesting designed ways. And you can even get as far as thinking about art, right? So there are people who are using what they call procedurally generated art using code to generate images like this. This is a mandala that's been generated procedurally in R, and other examples of art. And so if you look online, you can find whole communities of people doing this art. It's pretty fascinating, actually, and an interesting way of getting creative using coding. So the opportunities are more or less limitless. And you'll see it's really kind of up to you and your understanding of how to use the programming language of R and ggplot, as well as your creativity that's stopping you, versus more limited options like the kind of preset software. Like Prism is an example of a commonly used software that has limitations to what you can customize or do. And in the case of using programming languages, those limitations are pretty much gone. And so that's why we're teaching you it as a particularly good way to do your data visualization. What makes ggplot so great? Well, part of it is this sort of concept introduced by its creator here, Hadley Wickham, called the grammar of graphics. And so ggplot uses a consistent grammar that allows it to be a framework that is both kind of intuitive, but also very flexible. And that is kind of thought of in terms of layers. So the first layer of any sort of ggplot is always the data. The data is the start of the plot. You're layering everything else on top of whatever data frame you might be using to try to visualize it. On top of that layer, you have things like the aesthetics, the different scales, the geometric objects, lines, bars, etc., statistics or other changes to the coordinate system that are all layered on top one at a time, as you'll see literally in the code, to create the final plot. And so the idea of this grammar is that it makes everything consistent and flexible, and so you can easily change out individual layers to kind of customize your plots or to reuse code. That makes it very easy to make changes or tweaks to your graphics over time to improve them. And so here's an example of layers, right? So this scatter plotter is actually made up of multiple different layers, if you think about it. One layer are the geometric points here. Another layer might be the axes. And a third layer is the whole background of the plot, including the title. What is the color of that background? What does it look like? And each of these are layered together to make the final product, which is this plot. And we'll see how that works in the code right here. So, anatomy of a ggplot. So anytime you want to make a ggplot object in R, the first thing you do is you use the ggplot function. So here's the ggplot function, and the first thing you need to feed it is whatever data you're using. And this is a data frame. So we talked about data frame objects in R in the last week. And you tell it what data frame to use, and you also use this function called AES. And we'll learn more about what this means in a second, but what it is basically specifying the X and the Y axis for now. And this is your first layer, and you can actually run this code as itself, and you'll see what you get is a blank plot, right? So it's not a completely generic plot, though. If you look carefully, you'll see that the axes here are actually customized towards the data that you're using. So this is a data frame that has a variable called A, a variable called C, as well as B and D, and you'll see in a second. And it's customized the axes to actually be the range of that data. So you can see here, these are not kind of generic. There's actually, the data is the base layer here. Then, when you want to actually add more layers, you do so using this plus operator. And this is pretty unique to ggplot. It's not used in many other parts of R or the tidyverse. But you put a plus operator, and then you add another function that usually starts with this prefix geom. And this just stands for geometric object. This is an example of one function called geom point, which makes points. And you can see that these are layered on top of that original blank plot. And you can actually add as many of these layers as you want. So here we've added a third layer. Now we've added a geom line function, which is just plotting a line on top of these points and kind of connecting each one of them. The order is important. The way that ggplot works actually plots things at the top first, and then everything else gets plotted on top of that. So the first layer, the second layer is plotted underneath the third layer, etc. That becomes important sometimes. And you can switch that around without really changing too much other than what gets laid on top of another thing. And you can add as many of these as you like. You can then start to add other layers. So other types of layers include things that may change the coordinate system. So this chord flip function here is being used to actually flip the coordinates of the entire plot. And so instead of having C on the x-axis, we now have A on the x-axis. And just a way to kind of quickly invert the way your plot is. It might be useful sometimes, as we'll see maybe in some of the activities or assignment, to display the data a little bit more intuitively or clearly. There's also these scale functions. They often start with scale X or scale Y and then underscore some other attribute. If you're using this for a continuous data, as C and A are both continuous, you can do things like set the limits and say, I want to actually specify what the limits of the x-axis are. In this case, it's been shifted over here to the y-axis, but you can say it's 0 to 100 instead of whatever the default was from before based on the data. And so each of these can be added on as additional layers to your plot, customizing it further. Finally, you can add layers called theme layers. So these all start with the word theme. There are different ways to do it. You can use these kind of preset. There's a list, as you'll see in the end of the lecture here, of preset kind of theme options, theme classic being one of them. And you just add that as another layer to your plot. And what you can see is that it changes a lot of the aesthetics of the plot. The background color has changed, the line thickness has changed on the axes, the font size has changed. Things like that get all changed pretty quickly and is actually extremely customizable. If you want to do it in a more customized way, you can use this generic theme function, and I'll show you a little bit then later about what that looks like. It gets complicated, but it's also very where you kind of get all the possibilities of what you can do. Okay, so setting properties in geomes. So you can change the attributes of a particular geometric object or geome layer by just simply putting in what we call arguments into the function. So this is done by saying I want the attribute color to equal red, and that will change all of my points to be red. At the same time, I can do the same thing with shape. In R, there's a list of possible shapes for points, and number 12 here you can see is a kind of a boxy thing. I've changed it to that as opposed to just a regular dot. And I've made the size a little bit bigger. And so you can see here in this plot that every dot has become red, is a box thing, and becomes a little bit larger. You can also map variables to the aesthetics of a geome using the AES function. So remember that function from before. It can be a little intimidating at first, but it's actually not that bad and becomes very useful when you do more complicated things like setting data to different channels, as we talked about in the early part of this presentation. So the AES function can be used to assign variables in your data to different things like position, X and Y, the color. There's a difference between fill and color. Keep those in mind. Fill refers to anything that's sort of a area. Color refers to often line colors. Shape, line type, size, transparency is you use the word alpha to use that, just something you have to remember, a quirk of ggplot. And even the group of how you want to group the data by maybe some sort of third category variable. So how you do this is, kind of the differences between setting a static attribute and mapping are shown here. So as we saw earlier in the slide, just setting the color to red or the size to 8 generates a plot like this. But if you use the AES function in that same geome point layer, you can say, I want the color to equal D. And in this case, D is a variable in our data frame, and it actually has two different categories, A and B. And you can see that now ggplot has recognized that in the data and has actually colored all of the A plots red and all of the B points blue. And I can also do the same thing with size. So I want size to be based on this third variable C, which is increasing as you get down this data frame. You can see the size of each point is different according to the scale here. It's all pre-generated according to what the data is that you feed it. So this is mapping data using the actual variables versus just setting a static attribute. There are actually different ways to map data. You can do what's called local mapping or global mapping. So local mapping is what I've been showing you during the past few slides, where you take a particular geome layer and you set the AES function in that layer itself. And that will only color that one geome or only apply to that one geome. So here, the dots are now colored by D, but the line is still kind of a generic black line. Alternatively, if you want to save, you could just kind of, if you want to color the line by D as well, you could copy this code into here and put it in geome line. But if you wanted to save some time, another way to do it is to put it in the original AES function you had in your first layer. And so what this does is anything that's set as the AES, such as the axes, for example, or now color in the original layer, is inherited by all later layers of the geome, the ggplot. And so you can see now both the points have been colored and the lines have been colored into two separate groups. And so it's a way to kind of save some time, not repeat your code, which is always something we strive for in programming. Saving ggplots. So ggplots can be stored as objects. As you kind of learned in the first lecture, every single thing is an object in R. If you want to, instead of just printing out like we've been doing, you can actually assign an entire ggplot expression to a variable. In this case, that variable is named plot. And then you can just kind of call that variable again, and it will make your plot. If you want to save that object, the best way to do that I know of is to use this function called ggsave. And to do that, you specify a file name. It can also include a path for where you want, what folder you want to put your file in, what the plot object is that you created, in this case plot, and things like height and width. It's important to look at what's generated in your file here, because it can often look different than the viewer in RStudio. The resolution is different depending on what your height and width are. And what you're seeing in the viewer kind of real time is not always representative of what gets saved. So you might have to go back a few times and change these height and width parameters and mess with the resolution a little bit so that you get exactly what you want, because it's always a little bit different. And unfortunately, there's no faster way to do that. Okay, so now I think we're pretty much near the end, and these are more or less here for your reference in the future. If you want to know more about what some basic geoms are, I don't think these are all of them, but these is a good number of the ones that are more commonly used. So you're welcome to come back to this if you need some ideas of what sort of geoms to use. The same applies for these scale and coordinate modifiers. These kind of lab functions are very good for doing text labels or individual axes labels. Scale, continuous or discrete, manual, color, changing the entire coordinate systems, or this idea of faceting. So faceting just means that you take another variable in your data set and you facet out three, or however many different categories of that variable, versions of that plot that, in this case, the variable is dose, which is either 0.5, 1, or 2. And you get not one box plot, but three, showing the data from all the things in dose 0.5 or 1 or 2 respectively. And that can be very useful, as you'll see in some of the activities or the assignment. Themes. So this is a little bit more detail about the themes. As I kind of said, it can get extremely complicated. You don't need to know all of it all right now to start. You can use these kind of preset, pre-built themes. Here's a list of them here. Theme gray is the default, and that's what you get, just without changing anything. I particularly like theme light. It's one of my more favorite ones. It's a quick, easy way to kind of get a nice looking plot. But if you want to just use the individual theme element, you can add that to your ggplot and then mess with all these different attributes. There's a huge number of attributes here, and this is a resource you can use to kind of get a sense of what they all are. You put that within the theme argument. The theme function is an argument saying, for example, axis text equals element text size 10. And this is just saying you want all of your axes text to be size 10. And so there's many different ways you can do this. Don't worry about it if you don't want to get into it right now. There's kind of this is where you start to get to the high level of customizability. Okay, as you're going through your data visualization, remember the pillars. Showing data honestly, thinking about the way people perceive graphs, reducing clutter, using color in a strategic way, and getting creative. A few notes: Googling and also ChatGPT now are your friends. It's important to learn how to Google things in coding. It's a skill. And now, in some ways, it's maybe become a little bit obsolete by the use of ChatGPT, which I'll talk about in a second. These are some resources online that you can go to for how to use things like ggplot or using sort of different data visualization techniques. Feel free to kind of explore online. There's so many things online for how to do this. So there's a lot of material. It can be kind of hard to get to, but here's a good start. A note on ChatGPT. I and all your instructors believe that it can actually be very useful for learning how to program. It's very good at that, and it can be a nice little tutor for you. If you have a problem and you want, not sure how to code a certain thing, you can ask ChatGPT, and it gives you a nice sort of explanation, especially for things that are maybe a little bit hard to figure out how to Google or maybe a very specific problem. However, this being a course for Emory, we do have to adhere to the code of ethics for Emory, right? So the expectation is that you are the one writing all of the code that goes into your assignments for this course. It's okay to get ideas from other places like friends or ChatGPT, but in the end, you honestly need to be able to feel like you were the one that wrote the assignment. Because in the end, if you just copy and paste things and don't ever think about it, you're only really cheating yourself. This whole course is designed to help you develop the tools to do your research. And the way to do that is to struggle through kind of the learning of how to code. And without doing that, you'll be really hard to kind of internalize a lot of this, and you'll find yourself in a place where you can't do all the things you want to do. So kind of take this semester to go through the struggle a little bit. You can use ChatGPT when you get stuck, but make an honest effort of it. And we expect that of you in your assignments. Okay, that's the end of the lecture. There are, like I said at the beginning, another video going through the in-class activities, looking at a couple data sets that are pretty fun and interesting. And don't forget your assignment is due next week on Wednesday, using data visualization on the Pokemon data set. If you have any questions, feel free to reach out on Slack or email or Canvas. I hope you got something out of this or use it for future reference. So thank you all. Bye.